We're here at our last day of RADAN training. To recap what we've done so far, we started with a discussion of GPR theory. So we discussed why the image looks the way that it does. We broke it down into scans and samples and discussed what's contained within each sample, the two-way travel time and the amplitude to get to that sample, and how that's represented on the screen. We also discussed the parameters that are important to us when we're setting up our GPR. These include the dielectric constant, the scan density, or the scans per unit, and factors that affect signal quality like outside interference, cellular and radio interference, as well as the environment itself, whether or not it's conductive, saturated, or clay-rich. After our discussion of the foundational theory, we started looking at our 2D processes in RADAN 7. We've gone through a great deal of the processes in the processing pane to get us prepared for our 3D analysis yesterday. Yesterday, we built a few 3D grids in a variety of different ways, discussing the pros and cons of each, when to choose 3D batch of files, when to choose 3D file, and when you may want to use Super 3D. Now, to wrap all this up today, we're going to touch on a few topics that we haven't gotten a chance to touch on yet. We're going to start with another 3D grid pre-assembled and use that as a jump-off point for 2D interactive. So 2D interactive is a ribbon, an entire ribbon in RADAN that you can use to draw in targets, features, layers in your 2D profiles. They don't necessarily need to be developed into a 3D grid. We can use 2D interactive for individual files, but in our case, since we have it built into a grid, we can view those targets as they're being drawn out in our 3D grid. It's pretty cool, and it allows you to get a more precise position for your targets. As we saw with 3D free draw, when we were double clicking on the edges of each target, where you double click, it does latch to the highest amplitude it can find. But when you double click and attach the other end of it, you might be missing some of the variability in depth as that target goes from one end of the grid to the other. So 2D interactive can allow you to get a more exact position, and it's also the tool to use when you're drawing in layers or changes in material. The 2D interactive ribbon is a ribbon that's used frequently in our road scan and bridge scan applications, but it's also great for cover depth, for concrete and utility analysis. So we'll take a look at that first. Once we start discussing 2D interactive, we'll then branch off to a couple of other topics. I still have two processes I want to talk about, and we'll discuss those in preparation for our final 3D grid. Okay, so I think we'll just get started with some more material then. So I think we got most of our folks in now at this point. Everybody should have recording permissions. So if you haven't yet already, please open up the RADAN 7 software. Let me know if you can't see my screen. I should have RADAN open. I'm sharing my screen at the moment, so you should see that RADAN 7 screen on my end. Okay. So if it's not open, please click on Global Settings to open up this right-hand pane here. We're going to need to update our source directory before we continue. I'm going to double-click on the term source directory. We're already in the GSSI sample data folder. You may still be in cemeteries, so let's travel back over to the GSSI sample data folder. And then we're going to go into this 3D Mesh Concrete folder right below it. I'm just going to double click on the first one, There's likely just the one folder. You won't have a proc folder unless you've already opened and started processing this grid. So just highlight the 3D Mesh Concrete Grid 9. And then click OK. All right. So this is a pre-assembled 3D grid, which means we won't have to walk through the assembly process here. But don't worry, we'll get plenty of practice with that with our next grid. So at this point, now that we've updated our source directory, again, just for GSSI sample data, we're in the 3D Mesh Concrete Grid 9 folder. We can then head over to Home and click on Open. You'll see all of the individual DZT files here. And then down at the bottom, there should be just one Grid 9 B3D file. I have the DZT and the M3D since I've already opened this grid once, but you likely won't have these two files here. That's okay. We just want to double click on this B3D file, which will tell RADAN to grab these 22 other files and put them together into our grid. All right. So we have another grid open. Oh man, I'm in weird units again. So I'm working in feet horizontally and meters vertically. Let me just switch that. So I'm heading over to view. I'm switching my vertical units from meters to inches. And I'll stay in feet horizontally because I think this is a 10 by 10 foot grid. Right, so taking a look at this file, we can guess pretty confidently that this was collected with a SIR 3000, judging by the position of the direct wave, 4 or 5 inches down below 0. But let's confirm that by taking a look at the file header just to see what's been done to this grid already. So we look over here, we see this was, collected with a SIR 3000, some base parameters, 60 scans per foot. This was collected with a 2.6 gigahertz antenna. So this would be our Structure Scan Pro system with the blue hand cart and the antenna velcroed to the bottom of the cart. And then if we look down at our processing history, we see that we have quite a few filters that have been done to this. The default filters for our high frequency antennas on the SIR 3000 use a combination of both an IIR filter and FIR filters. So that's why there are 3 separate vertical filters here. This is just the factory default for this particular antenna. You can mix and match these filters. It's generally okay. You won't see much of an issue there. I am going to have us reapply IIR filters to make this image look a little bit better. It's my opinion that the default filters for the 2.6 need a little bit of extra work to get the image looking as good as possible. So I will let you know what that is when we get there. But other than that, there hasn't really been anything else done to this. So this is a pretty raw grid with the exception of our high pass, low pass filters. So we're going to need to throw basically the whole kitchen sink at this. So I am going to slowly go through and process this grid. I encourage you, if you already have a game plan in mind, to start having at it. I will start processing this as well. And then once we get it ready for 3D, that's when we'll start discussing 2D interactive. So it's definitely best to pre-process this a little bit prior to using 2D interactive. You can use 2D interactive before or after a migration. For this grid, because it's fairly straightforward, we mainly just have reinforcement. It won't really hurt us to do it after migration, but I'll explain why that's a choice when we get to discussing 2D interactive. So for now, I just want you to process this grid, and I will be telling you why I'm doing certain things as I go through and process this grid as well. Stop when you get to the IIR filters. I want to walk you through my decision process there. It kind of plays off of what we've discussed already, but I use a different filter than what you would calculate just by taking the center frequency when I set my filters for this particular antenna. So why don't we just get started? We're going to head over to, well, I'll close the file header. I don't need that anymore. And I'll probably head over to my color tables and color Xforms first. Color table, I'm still using 18. I'd recommend sticking with a non-gray for this one. Color Xform, I'm on LM4. It's very good for concrete. I'd recommend using either LM8 or LM4 for any concrete data. And then once we have that set, we can head over to processing. We're going to start with time 0. I'm a fan of the auto peak method, so I usually just double click on method. When you double click on these parameters over here, if it has a drop down window like this one does, anytime you double click, it'll just move down to the next option. So scan by scan, H drift, so on and so forth. So that's usually what I do here. Auto peak works fine for me. I'm going to click OK. It's going to scroll through your grid, apply that correction, and then give us a newly processed grid. Okay, so now let's talk about our high-pass, low-pass filters. That's probably what we're going to want to do next. And in general, I would recommend for a grid that needs both high-pass, low-pass filtering and range gain, you might think that range gain would be a better option so that your scan is brighter and easier to see, which might make filtering out the noise easier. But I find that I get a better range gain curve after I filter out the noise. You don't want to accidentally gain up that unwanted signal interference that you're going to remove anyway. So my thought process is I'll filter out the noise first. It might be a little bit harder because it's not as bright as I'd want it to be, but I can counteract that if I really need to by adding display gain. And then once I filter all that out, then I can range gain and get myself a nice bright image that looks good for the already clean data. So we're going to head over to IIR. Vertical, low pass, and high pass. So for the low pass filter, if we're using a 2.6 gigahertz antenna, the low pass would be 2 times that center frequency, which is 5,200. 2.6 gigahertz is 2,600 megahertz. I'm just going to even that out to 5,000. So I set 5,000 as my low pass filter. My high pass filter, if we take 1/4 of that, that would be a little over 600. It would be 600 or 700. I usually set this to 1,000. I've found that setting it pretty high, up to 1,000, will get me a much better representation than the calculated default. The default's even lower than 1/4 of 2.6. I think the default's around 400 or 500. But I found that with a very high pass filter, one set to 1,000, that the 2.6 gigahertz data looks much better. And then we'll set our number of poles up pretty high. Let's shot that up to 12. 12 looks pretty good to me. And then if we hit apply, you'll notice, here, I wonder if I can do this. Okay, so if you look at this wave, if you look at this image, you'll see that there are these pockets of really strong negative amplitude and really strong positive amplitudes. It's sort of like a thick band of positive that washes over the data, and you'll see it down in deeper places as well. I see this a lot with the 2.6, and that thick banding can be filtered out with a more aggressive high-pass filter. It gets rid of that, whitewash effect, and makes the image look better. So that's ultimately the goal here. Right? This is before and after. We see a pretty nice improvement, especially where our wire mesh is, because this thick positive band cuts right through our reinforcement. So I'll click OK here. This filter is going to scroll through our file. And the grid is so small that I don't even really need to worry about making the tables and file header window show. I'm just hitting the process and letting it run. But if it's taking a little bit of time on your end, remember that you can open the tables pane and you can open the file header to shorten this grid, and that'll speed up your processing. Okay, so just a couple more things to do. We still have this direct wave at the top, so I'll get rid of that with noise band removal. It didn't do a great job getting rid of that banding. Usually it does a better job. Let me try a different one. I'm going to head back to the previous instance, so the tab right before it, and I'm just going to see what a vanilla background removal does. That actually does way better. So I think this time, it's one of the few times I'm going to choose background removal instead of noise band removal. Just does a better job getting rid of that banding at the top of the screen. It's okay if it's there. We don't really have any data that close to it. This is probably the closest we get, but I generally don't like it to be there. So background removal will do a better job at that. Okay. So at this point, we have gotten rid of most of the noise. We've taken care of ground surface. So now let's brighten this image up. It looks pretty good with the amount of display gain I have on it, but I'm going to take that off and we'll see what we can do with range gain. So I'm going to head over to processing, range gain, exponential gain type. Probably 7 is all I need here. We don't have a whole lot going on here, so it's a little too much. Remember, with range gain, we're just doing 1 or 2 points at a time. Make sure to test it on multiple files before you hit the OK button. If you hit the apply button, you'll see that there's this big washed out region at the very bottom. This is actually where the bottom of the data was. And we see this washed out area because Pretty sure this takes up the exact same amount of space that we removed up top. So that blank space up top has now been moved, quote unquote, to the very bottom of the screen. All right, this looks pretty good to me. It seems to work well on most of our files with our higher targets and our deeper targets. So I'm going to hit OK. Okay, so we've taken care of time 0. We've filtered out our noise. We've gotten everything brighter. All that's really left for us at this point is migration. So I'm going to head over to a file that has nice clean hyperbolas. You can really pick any one. And then we'll head over to processing and select migration. Again, we're using this tool to fit to the arches that we see. The default actually looks pretty good, and actually I don't think I need to make any changes. The shape looks fine. The horizontal bar distance also looks fine, so let's just see how that is. Close. We'll see some slight upward movement, right? Very light, but there are some tails that point upwards, and I know we can take care of that. So let's try a slightly higher dielectric constant. I'm just going to type in new values at this point. It's easier for me now. We'll bump that up to 9, hit apply, and yeah, that looks good to me. Maybe just a little bit higher. Let's say it's like 9.25. You're just on 5, 9.5. Okay, cool. Scroll around to a couple of different ones. This is a any guesses what might be happening here? Why this area looks so much busier than the area next to it? So I'll give you a hint. This is wire mesh reinforcement. Very quick way to tell that is by looking at how different the depth is as we go over this site. It gets much deeper and then much shallower over a very short 6-foot distance. Usually rebar remains fairly consistent in its depth over large areas. Wire mesh generally changes its depth dramatically over a small period of time. But this is actually where one wire mesh ends and another mesh is beginning. So we're seeing two overlap one another here. But if I hit the apply button, we can see where each and every individual piece of wire is much more easily. Pretty cool. So this looks good to me. I like this dielectric constant. I am going to add some extra gain to make this a little brighter. Maybe I'll just go 10. Cool. Okay. So this looks good to me. Yep. So let's hit OK. All right. So now we're going to start getting to some new stuff. We fully processed this 3D grid. We will take a look at it in 3D, but I also want to use this as an opportunity to discuss 2D interactive. So we fully processed this grid. Now let's take a look at some new stuff. So While we discuss 2D interactive, I think it'll help us to have the 3D view data window open. So I'm going to close processes because I no longer need it. And I'm going to open the 3D view data window, which brings me this nice grid over here. So I'm just going to stretch it out by holding Z, pressing the up arrow a few times. A little bit more. Cool. Add a little display gain. And then, yeah, we can start slicing up and down through. We should see some pretty nice reinforcement on the screen.
Hey, Kevin.
Hey.
My grid crashed. Give me a minute to get back up to you, will you?
Okay, sure thing. All right. So we have our grid here. I'm just slicing up and down through it just to get a look at the data. You should see some wire mesh that's brighter in some areas, dimmer in some others, because again, the depth is changing over the site. If we look over here in our Windows settings pane, so I wanted to talk about some of the other Windows settings as well. We discussed X, Y, and Z position. We talked a little bit about thickness. You also have a 3D Z slice mode. I don't use it too often, but if you toggle this on, it will attempt to, oh, interesting. Okay, that's new. Okay, so it's working differently than how it worked in the past. It actually does the exact same thing that the next thing I was going to show you does, and that is down here in XYZ visibility, the transparency and see-through functions. So it looks like 3D Z-Slice mode has changed into a see-through function. That's pretty cool. So as you slice up and down through it, you should see your high amplitude targets showing up through the grid, basically drawing in all the reinforcement for you automatically. If you want a little bit more control over this view, you can do that instead of here using one of these visibility functions, transparency or see-through. So I'm going to start with see-through because it's a little more straightforward. If you double click on see-through, toggle that on. And what see-through does is it shows you just your high amplitude targets that pass through a specific threshold. So this number here corresponds to a percentage between 0 and 100. And the higher this number is, the brighter targets need to be to show up on the see-through view. So another way to think about this is the higher this number is, the less congested your picture will be. So if you are seeing not just your rebar or wire, but a bunch of background noise, you can increase this threshold to hopefully filter out that background noise and just see your high amplitude targets. If you decide to change the threshold, don't use the up or down arrow keys here. Every time you change it by 1%, the whole grid has to reload, and it can really slow you down. You also usually won't notice much of a difference when you change it by a percent. So when I want to change this, I usually just type in multiples of 5, right? So if I have too much and I want to remove it, I can erase this and type in 30 instead of 25. That seemed to have been a little too much. So nothing else is on the screen now. I'm going to try it with a lower number, maybe 20. Okay, now that's looking a little better. looks like the default view is showing me a little too much. So a couple of other things to note about this. This see-through function will display differently on different, how else do I want to say this? I want to say this differently. I guess what I'm trying to say is your grid might not look like my grid even though you have the same threshold. And that is because this threshold is dependent on the gain in the grid, which is dependent on the range gain curve that I made, which might not be the same one that you made, as well as any display gain that I've added. And in my case, I also added some additional gain in migration. So all of those gain values combined will give me a different picture when I have different threshold numbers. So the fact that your image doesn't mimic mine might just be dependent on how I have my grid set up. Little numbers. Anyway, this is how the see-through function works. It works pretty well. It's actually working very well for this grid, and it usually does for concrete. If you would rather see everything in your grid that makes it through a specific threshold, you can try using transparency instead of see-through. If you decide to switch between these, just make sure you turn the other one off before you turn the other one on. So I turned see-through off, and then I'm going to turn transparency on. Yeah, so we have that pretty low threshold number, which is why I'm seeing a bunch of stuff. Let me try a higher number, 15. That looks a lot better. Might actually been a little too high. Okay. So this is what transparency does. It can give you a general sense of how depth changes as well, because it splits your data into multiple discrete slices. You can stretch them out if you want. What I sometimes do for pictures is I compress it together just to get you that top-down view. But these are just different ways of visualizing your data. They don't work super great in soils, which is why I didn't really show them to you yesterday. But they do tend to work very well in concrete data sets. So I'm going to turn transparency off, and we're going to now take a step back over to 2D interactive. So we've discussed some ways of visualizing our targets using different see-through or transparency functions. But if we want to actually draw them out, we really have two options. We could use the free draw tool that we discussed yesterday using this pencil icon where we can double click on either side of the target, or we can draw them in using our 2D data. So that's the method that I'm going to show you next. I'm going to head over here to 2D Interactive. And in the 2D Interactive pane, I see that I have a number of different picking tools. Currently, my picking tools are disabled. And then the other tools at my disposal are Single Point, Select Block, Select Range, Ground Truth, and Easy Tracker. We're going to start with the Single Point picking tool. So when I click on Single Point, you'll see over on the left, after you click on your file, that the Objects and Pick Attributes pane become selectable. So what these are telling me is with my single point picking tool, anything that I click on with a left click, I'll add a dot, and that dot corresponds to a target called rebar, and the dot is placing itself at the highest positive amplitude it can find in a search width of 9 scans. If you were looking carefully at the data as well, you might have noticed that when I left-clicked, a single pink dot showed up on my grid. We can keep drawing that target out. If you head over to line 2 and left-click again, it will connect the dots, and it will continue to do that until we hit new target. Right, so maybe I think I've finished adding this target. I can click new target, maybe head back to the first line, and then do it with my next one. And I wasn't actually following something there, but if I left click there, I get another dot. And then I can continue, probably not doing one at a time, but moving a couple of files and left clicking just to get a general idea of where the target's going. Looks like I went over to the Y direction accidentally. But this is one way to draw in targets and features. You will have all of this data in another tables pane. So if you want to delete individual dots, you got a couple of ways to do that. You can open your tables pane. Mine's still huge. You have a target picks table. And if you want to get rid of specific points, you can right click on them, hit delete. Those picks will go away. Another way to delete picks is to go to your data, and you usually have to left click again to get the 2 vertical black bars to reshow. You can right click over the dots to delete those picks as well. I think I need to be on the last dot to do it. Oh, I'm not focused on it, that's why. Okay, so I'm trying to delete one from the previous target, and I need to switch my focus to that target so that when I right click, I delete it. Right, this focus option is very important when you're drawing in features. If you want to affect a specific target, you have to make sure that you're focused on that target. Okay. So this is a way to add in one target at a time, drawing in individual targets. If you have a large section of targets that you want to draw in, and you don't necessarily care if they're all considered different targets, you just want the points to be there, you can add those points using the select block or select range tools. Select block allows you to click and drag on your data to create a block. You can adjust the size of it by clicking on these boxes on the top and corners. And then once you have your box around the area that you want to affect, you can right click it. You can add points to it or delete points from it. So if I do new target, I just call them all rebar 2, and then I click add points. I will add points in here. And it'll attempt to place dots at the high amplitude targets it finds using these attributes. By default, we're just doing a positive polarity addition. If you are trying to pick voids or air-filled targets or features, you can also switch your pick polarity to negative. You can just do the absolute value, where it'll place a dot at the highest positive or negative amplitude it finds. Or you can switch it to none, which means the dots will go right where you click. This is really only helpful if you're using the single point tool. You can also use select block over the entire grid, which is precisely what select range is used for. Instead of selecting a block just on the one file you're looking at, when you use select range always goes to the very beginning of the file and then all the way to the very end of the file. And for grids, it also goes everywhere in this grid. So this might crash RADAN, but we'll see what happens. If I click new target and I right click and I just say add points, it's going to attempt to add a point everywhere in the grid at that specific depth. Yeah, okay. And then I can, of course, delete points that way as well. Okay. So the last two picking tools that we have are Ground Truth and Easy Tracker. Ground Truth is a picking tool that you would use if you know the depth of a specific target you're looking at. So let's say I click on Ground Truth and I actually drilled down to this target and I confirmed how deep down this target is. Let's say I know it's exactly 5 inches down. I can select the Ground Truth picking tool. I can left click right on that target. I want to be focused on that target, and that is probably, let's see, rebar 2. Okay, rebar 2. So I'll focus on rebar 2, Ground Truth there, and then I left click. And I see that this target I know is exactly 5 inches down. Then I hit OK. Small black box can go over that. We actually even get a black crosshair in our 3D grid as well, indicating where our ground truth point is. Very cool. And then I can head over to target ground truth and see that, okay, with this information, with this ground truth point, I see that this corresponds to a layer dielectric of 7.97. I can change the depths of my targets using this if I so choose. There are two ways I can do this. I can either go to the file header and just type this new dielectric in, or I can go over here to target picks and I can change, or targets rather, and I can change what velocity method I'm using to calculate depth. By default, it'll use the default dielectric constant, which is 7.4. But if I want to change it to some other number, like using my core data, for example, I can switch this to core data. So core data corresponds to ground truth information using this target ground truth pane. So if I switch all of my target velocity methods to core data, that means it's not going to use this dielectric, it's going to use this dielectric constant. You can also have it use the migration constant, which is the constant we got from migration, and that is done using velocity analysis. If you switch the velocity method to velocity analysis, That means we're going to calculate depth using the constant we got from our migration, which was about 9.5. But for our cases here, I'm going to switch this back to default. Okay. So any questions about these processes so far?
Kevin, I have two questions. So first one is when you are doing this 2D interaction, there's a pick type. One is target, another one is called layer.
Mm-hmm.
So what does exactly do with this layer?
Yep. So layer additions are what the Easy Tracker tool is used for. If you have layers in your data, right, so if I go back over here, I still have ground truth selected. I hit cancel. So if I have layers in my data, I can click on Easy Tracker. I can switch my pick type from target to layer. Notice the tables pane switches to layers automatically as well. Now it's layers, layer depths, layer pick details, layer ground truth. My focuses are now layer 1, 2, 3, 4, 5, 6. Easy Tracker is meant to help make picking layers easier. You start it, you click on it to begin the process. You click start to actually start adding your layers. And then if I left click, it's going to place a dot on my screen. And then if I left click next to it, it will attempt to connect the dots. And if you have a clean layer, those dots should go in the high amplitude line that your change in material appears as on the screen. So there's like a kind of a positive band I'm trying to follow here. It's not a layer, which is why it's not doing a great job. But as you left click, it will start adding picks in there and it will connect the dots. If you would rather it connect the dots in different ways, you can change that using global options. Global options allows you to change your interpolation method from automatic, which is what it's doing right now, to nearest peak, which means it's just going to use the closest peak and then continue that process to get to your next click. Linear does a straight line interpolation. So if I switch it to linear and then I click OK, and then maybe I focus on layer 2, left click, left click, left click. Another thing to note about Easy Tracker, these layers will not appear in your 3D grid. So at this time, we don't have a way to show surface changes or layer changes in our 3D grids. So the pixels still remain here. You can still export these pics out of RADAN into Excel or a CSV document for further analysis. But these will not be visualized in RADAN. It's just the target pics at this time.
Okay. So my second question is, let's say, field crew, they went to site and they forget to calibrate the dielectric or they use wrong dielectric. And we end up getting a different depth coding versus, from the GPR. Is there an easy, like one click, fixing? Because I have the core depth, yeah, and I have the scanning depth, which are different. So is there like one other than dielectric you showed earlier? Is there any other way I can do it?
So the only way that you can really apply that core data is to know where to apply it in your GPR data. So if you have a core and you know where it is in your radar data, the best way to apply it is to use this picking tool, click on the point, and then switch your velocity method to using that point. If you would rather just set it for the entire file, you can look in the tables pane, see what that dielectric is, and then just head over to the file header and type that new number in over here.
Oh, okay. Cool. Thank you.
Yeah, no problem.
Hey Kevin, so if you do that, if you put the depth on your target pick or whatever target point, will the target points move up or down based on the depth? Like, would the depth adjust once you adjust the dielectric, or?
So I see where you're getting at. So they won't shift visually up here. The only place that they shift visually is in this depth pane data window. The depth pane data window shows like just the picks that you've added and then any other information you might have applied. This black dot is where the ground truth pick is. And if I go over to 2D Interactive and I use single point, and I switch this over to target again. Let's see if this works. So if I switch that to core data, you might see these picks shift a little bit. Depends on if I pick the right one. Okay, not yet. Okay, one of them shifted, and then the rest of them should shift. Yeah. So you might have noticed they all shifted up a little bit.
Okay.
And then when you export the depths of your target picks out, for example, as long as your velocity method is set to core data, and as long as you hit the save button to save that change in, when you export this out into a CSV, you should have those calibrated depths in there as well.
Okay, thank you.
Yeah, no problem. And generally, hitting the save button isn't something we need to be that concerned with most of the time, because usually we apply a process and then the new file is saved anyway. But when we're doing these target additions and adjustments in the tables pane, it doesn't get saved to your data until you perform a process and open a newly processed grid. And if we're not doing that at this stage, which generally we aren't, it's important to make sure that you hit save before you export anything out. Otherwise, those changes might not be applied. So it's an important step that I don't think I push on too much. Okay. So I have one other thing that I want to talk about here before we at least take our morning break. I'm going to close some of these windows because my RADAN window looks really busy right now. And I don't need all of this on the screen here at this time. I am going to go over to, you know what, I'm just going to go over to the previous version of the grid. So the tab right next to it, the unmigrated view. And I'm just going to migrate this again to give us a second grid to work with, because I don't want to have all of my target picks in here. I know I can get rid of it just by clicking on these, but I think it'll just be easier to remigrate. So I'm going over here. I'm going to head over to processing, and I'm going to click on migration. It should be already set and ready to go with the dielectric we were using. So as soon as I click OK, it should process and give me a nice migrated data set without any drawn targets added in. So we're going to talk about the last process we might want to do here. This is one of the few processes that you may do after a migration. And this process is called Hilbert transform. This is a process that you may have unexpectedly seen many times before in our systems without you even knowing it. The Hilbert transform process is something that we do most of the time on our control units before showing you your 3D grids, because it can make the 3D picture look a little bit better. If you've ever viewed a 3D grid that's been collected on a SIR 4000 or StructureScan Mini, you've seen Hilbert transform before. If you've ever used the focus views on your utility scan or Mini XT and you've switched it specifically to Focus Plus, you've seen a Hilbert transform before. So let's talk about what a Hilbert transform actually does. If you click on the process, you'll see that this is another pretty straightforward process. We have a scan representation up here, which looks a little strange. And we really just have one thing that we can make adjustments to. We can either transform to magnitude, transform to phase, or transform to frequency. You will likely never use these two. Transform to magnitude is the only one that we really do. We do a magnitude transform for showing 3D grids, and you may want to do a magnitude transform to view your own 3D grid. So let's talk about what this process actually does. If you've ever looked or paid close attention to the appearance of your dots on the screen, or even the appearance, oh, that was the previous version, or the appearance of your hyperbolas on the screen, you've probably noticed that when you get a reflection from something, that reflection is made up of not just one band, but 3 bands. Usually you get a distinct, for metal targets at least, a distinct positive band with a negative band above and a negative band below it. So this negative, positive, negative triple band. When you migrate these hyperbolas into dots, you also get a triple dot, we'll say. That is positive with a negative band on either side. What a Hilbert transform process is able to do is observe that that is all coming from the same target. This positive, this negative, positive, negative band is all coming from the same thing. So instead of showing it with 3 different phases, we can flip those all to their absolute value, positive, and showcase it as one uniform positive reflection. I will say that it takes some getting used to looking at your data this way. I myself still usually prefer to look at my data in this manner than I do in the Hilbert transformed manner. But if you're not really going to do any 2D analysis, you just want to observe your 3D grid or maybe create a 3D picture for a customer, the Hilbert transformed data will show better in 3D than the non-transformed data. So it might be worth doing, but I would say only if you're not intending to look at or analyze your 2D data any further, because it is going to look a lot different than what you're used to seeing. So if I head over to processing, click on my data to re-highlight this, click on Hilbert transform, and then we can just hit the apply button to see what it does. You'll see that, yeah, everything is now positive. It also looks a lot blurrier than it was beforehand. But the intention for this is not necessarily to make it easier for us to look at in 2D, but rather to make it easier to see in 3D, or overall to just make the 3D picture look better. But that's really it for this process. There's no real adjustments we need to do, no real tweaking involved on our end. You just, if you want to do it, you click on the process and click OK. If you don't want to do it, you skip over it. It does make your 3D grid look a little bit better. At this point, this data was already pretty clean, so you're probably not going to notice much of a change after applying this, but that is the ultimate goal. That is the ultimate intention for this process. We can hit OK just to see how it looks in 3D. And then we can pop open the 3D view. Right. As I said before, it was already a pretty clean grid, but it should make it look a little bit nicer. Okay. So it's about 5 after the hour at this point. I still have a couple of other topics that I wanted to discuss. We're going to talk about one more process, and then we can make use of that process as we go over our last 3D grid. And then from there, I'm going to open up the floor to just general questions. So if you have some data that you want everyone to take a look at, if you have another process or two that you want us to review or go over in more detail, that would be the time to do it. But I think we're just going to take a quick 15-minute break. So I'll be back with you in 15 minutes, which will be 20 minutes after your current hour. So 20 minutes into the hour you're currently in, I'll be back with some more new material. See you guys then. Now what I'm going to touch on next is a new process. So we just discussed Hilbert transform and when you may want to use that. And next we're going to move into discussion of the final process, deconvolution. For this process, we will need to change our source directory. So I'm going to ask that we close all of our currently open data. I'm going to head over to the G button and click on Close All Open Files. And then I'm going to bring myself over to Global Settings, to the source directory. And I'm going to change this to the GSSI sample data folder. So we're actually just going to bring that up one to GSSI sample data. And then we'll click OK. All right. So we've updated the directory. We don't have to worry about units because we're just looking at a 2D file. So we're going to head over to Home. We're going to click on Open. And we're going to open the second to last file, Tanksinwater. All right. So let's talk about, I guess, first what this file contains. If you couldn't tell by the name, this file has tanks in water. We have 3 big tanks in fresh water, and a data file was collected over top of these tanks. I haven't actually seen the site where this was collected, but I have to imagine there was some, like a wooden cover over these tanks or plastic cover over these tanks, over the water that these tanks were in, and the radar was pushed over top of it to collect data perpendicular to these. If you look very carefully, and by knowing what is in here already, you can start to see a faint hyperbola over on the left, and then there's another one over on the right in a similar location, but These targets are definitely hard to distinguish because of the presence of these thick positive and negative bands that overlap everything on the screen. And it's precisely this form of ringing or repeated reflections that we get from very strong reflectors, like a freshwater interface that's right underneath the antenna, or a steel plate that we might travel over out in the field, that just rings all the way down through the file in a specific location, not necessarily consistent across the entire data set, but maybe a narrow band that just rings all the way down through your file. It's this precise form of interference that a process like deconvolution is meant to remove. Deconvolution is a process that you set to what we call the pulse width or operator length of the antenna. So we're actually going to need to take a look at the scope view, the O scope view over here, and use that to determine the operator length. This is the key parameter we're interested in here. And then once we have that knowledge, we can head to the processing pane. We can open the deconvolution process, and we can start making adjustments to that process to try to filter out this ringing, this consistent banding that we see on the screen. So if you're out in the field and you're collecting data and you see consistent ringing in these locations, maybe by going over a steel plate or a particularly strong reflector or interface that was very close to the surface, deconvolution would be a process you can use to remove that ringing. It's going to do a much better job than something like background removal might do. In this case here, because the banding takes place over the entire file, background removal does a fairly good job. But most of the time when you have this ringing, it's constrained to a small section of the file. So processes like background removal might not catch that. It's situations like that where deconvolution is a good process to add into your sequence of processes. So now that we've talked about how it works and roughly when we'd want to use it, let's actually get down to using it. I told you that we need a parameter called the operator length. The operator length is a pulse width from two common polarity bands in a single reflection off of the antenna. So in order to obtain this information, we're going to need to head over to the home ribbon. We're going to need to open the scope data window, which I have right over here. And what we need to find in our data is a reflection from the antenna that is not in the ringing area. So if we're doing this out in the field, we would just go to a part of the file that doesn't have ringing in it and look for two positive amplitude reflections or two negative amplitude reflections that might be around a real reflection received by the antenna. This could be a rock, this could be a utility, this could be the feature we're serving for. You want a real reflection with three bands that you can find the width of, basically the wavelength of. But we need to find the wavelength of this in not time or depth, but in units of samples. So that means not only do we need to have the scope on the screen here, but we need to switch our vertical scale from depth, which is where we currently are, to samples. This can be done in two places. You can either head to the View ribbon and click on the vertical scales to switch it from depth to samples, or the quicker way to do it is to simply right-click in this corner here, and when you right-click up here, you can switch it from depth to samples. Now, as you click and drag and move your mouse over the screen, if you look carefully at the bottom of your RADAN window, you'll see that Z equals a sample value, SMP, and not a depth, like feet or inches. So then I'm just going to click and drag and move this around until I get a nice waveform to use. Now, the waveform we're going to use here is actually going to be from the direct wave, because that's the only part of the reflection that hasn't been really impacted by this interference. So this is actually really the only process I would do before time 0, at least for SIR 3000 based data. But if you're using SIR 4000 based data, or you're doing this elsewhere out in the field, you generally wouldn't be doing it in a situation like this. You would have some ringing, but you would also have some real targets that you can do this with. This is a very special case where almost everything has been affected by this noise, and the only thing safe from it is that first reflection between the transmitter and receiver. So we're going to use this here. And specifically, I'm just moving this around until I have a fairly uniform wave to work with. And this looks pretty good to me. So once I have it set over here, I'm going to move my mouse over here so that when I click and drag, I don't update this as I move around. Now, when we're getting our operator length, you don't need to be too stringent on this. This gives us a place to start, but we're definitely going to change it a lot to get this process to work well. The operator length just gives us a starting point rather than typing in numbers blindly. So I'm just going to round it. I'm looking at the Z value of the very middle here, and I'm seeing that it's about 65 samples, sample 65 rather. And then if I go down here, I see that I'm at about sample, we'll just say sample 90. So I'm going from 65 to 90. So that would be an operator length of 25. So I now have a place to start. We're going to write that number down, or just remember it. That's the first number and really only number we need to pull out of this before we open the process. And now that we have our operator length, we can head over to processing. We probably need to click on our data to get it back to normal. If you don't want to be in samples anymore, that's okay. We can right click on this and switch this back from samples to depth. And then we're going to click on deconvolution. When you click on deconvolution, the deconvolution process will show up. We have a few channel parameters. These are the 4 that we'll be working with. I really only change 3 of the 4. The pre-whitening percentage I generally leave alone. But the operator length, prediction lag, and overall gain are 3 parameters we're going to want to adjust. The operator length is that one that we just worked to get. So let's start with our calculated one, 25. We're probably going to need to change this. Usually I find that this process works better with bigger lengths, but we'll start here. Now, I told you that trick with the info tab. You can click on these here and it'll give you a little bit of information about it down below. Sometimes it's more helpful than other times. But for the prediction lag, if you're reading that, you'll see that usually you want to start with half the operator length. I have found in my own practice that small numbers, really small numbers, work better. So I usually leave this set down to 5. Usually I'll switch this between 3, 5, and 7, and one of those will usually work well for me. The operator length I generally set to bigger numbers. I think I've set this upwards of 40, maybe even 60 in the past. But this is in my opinion, definitely a guess and check process where I'm going to try different numbers. We want to try to remove these thick bands, but we don't want to. You can sort of overdo this where instead of making the bands less pronounced, you make them more pronounced. So we certainly don't want to edge on that territory. We want to try to get rid of these bands and keep the rest of the data intact. This is also another process that weakens your scan by a lot. So I usually bump this from 1 to 2 or 3. You see the scan gets much bigger when you do that anyway. And let's just see how this first one works. I don't think it's going to work well just looking at the scope. So let's hit apply. And we see that, it does tighten it up a little bit. It does make this look a lot better. It does make these look a lot better, but that banding is still there. So I would say off of this, it's an improvement, but I think we can do better. So we're seeing some slight improvement here. Let's try a bigger operator length, maybe 30, or I'm looking at this here to see really how well we're doing, and maybe 40, and then maybe a prediction lag of, nope, that's way too low. Yeah. So set that to maybe 3. Okay, that looks a lot better. So that's actually pretty good. So that cleans it up by a lot. We're still not quite there. Big numbers. Trying to look at this here, and I want to pull this over, but I don't think I really can. So it's not going to work.
Hey, Kevin, this is Akash.
Hey.
I had a question. When you set up your operator length, are you looking to, is this like a filtering? Are you looking for waves within the wavelength of whatever you give, like 40, let's say?
So for the operator length calculation, that just really gives us a place to start. So this is something that I used to do a lot. I used to spend a lot of time really focusing on getting that operator length and getting that as a starting point. But as I've been doing this more and more, I'm finding that bigger numbers just tend to work better. So I think going through the effort of really calculating that might not be as effective as just trying different numbers and seeing what the result is. This is definitely a very guess and check process for me, where I tend to just try a wide range of values, and I'm keeping an eye on this scope view as I change those values. And if it starts to look a little bit more quote unquote normal, then I might change the values a little bit less so until I get the image that I want. So I guess long-winded way of saying there's a wide range of values that can work pretty well in here. So they don't necessarily need to be right at or in the neighborhood of the wavelength.
Got it. And I was wondering what it does actually to get us this better picture, like what the process is for the deconvolution using this.
Yep. So in the background, what this process is attempting to do is look at this scope, and what you're telling it is how big reflections should be, what the wavelength of reflections should be, and anything that it sees with a wavelength greater than that, it attempts to remove from the scope while leaving small fluctuations like this, for example, like a small fluctuation here. It'll keep that intact because that's smaller than the parameters that I'm inputting. So you're giving it a true reflection wavelength, and anything greater than that, it's attempting to remove from the scope.
Gotcha. Yeah, makes sense.
Yeah. That's much too bright. So I found that with that really big number, that seemed to work really, really well when I set it up to about 60. With a low prediction lag. And that seemed to do a pretty good job. It kept the tanks intact and got rid of the rest of the banding. So I think for this file, this is probably going to be the best that we can do. I'm going to bump up the overall gain by just a little bit more to make it a little bit brighter afterwards. Maybe instead of 3, I set it to 2.5. But I'm keeping that low default prediction lag, and I actually bumped the operator length up to 60, and then an overall gain of 2.5, just to make it a little bit brighter afterwards. The default of 1 usually makes it look much too faint. Interesting. Okay, so I'm going to click the OK button here at this point. To apply this deconvolution and to get us our fixed file. Right, so as we can see in the side-by-side comparison, prior to it, we could see evidence of some tanks in here, but after it, the tanks become much more well-defined and much easier to see. And that's really just the goal here, and the goal of any process in general, is to make the file easier to view and interpret. Okay, so now that we have this new process under our belts, let's look at one last grid to wrap things up. So for this grid, we are going to want to close all of our currently open files because we need to update our source directory. I'm going to open the global settings pane, and I'm going to switch the source directory to the GSSI sample data folder. Is that where we want to go? Yeah, we'll do the GSSI sample data folder, and then we are going to select the Etowa folder. So this is directly underneath the 3D Mesh Concrete folders. We're going to head into Etowa and then click OK. All right, so I'm going to open up the grid notes here just to make sure that we're working in the right parameters. I think the grid notes in the dataset folder are incorrect. So let me open up my version and I'll just walk you through that. I keep meaning to update that, and I will update that for the next class. Okay. So let me head over to Okay. So this is a metric grid. So after we change the source directory to Etowa, we are going to want to work in metric units. So switch your horizontal units to meters at the very least. I'm also going to switch the vertical units to meters. Okay. So horizontal and vertical units are both going to be in meters. And then once we have that set, let's head over and start assembling this grid. So this is a grid that we need to assemble before we can look at it in 3D. This is a straightforward grid. It was a square area. So we can do 3D file or 3D batch of files. I'm going to do 3D batch of files, but if you'd rather experiment with 3D file more so, feel free to. The dimensions are going to be the same no matter what. So I'm going to head over to the main button, go down to assemble data file, select 3D batch of files. In this first window, it just wants a batch file name, so we'll call this grid, and then hit next. You're going to want to click add all to add all of these files into it. I have one extra file, so I'm just going to remove that. It's the DZT from me building the grid earlier. But if you click add all, you should see everything from file 83 down to file 123, and make sure that it's in ascending order. This is another unidirectional grid, so the order here does matter. So then we'll click next. Give it some dimensions. Min x, min y are 0. Max x and max y are both 20. And then we want to group the files in the x direction. So file group in x direction.
File group in X direction, does that mean it should have been unidirectional in the PDF?
Yeah, so the PDF is wrong. I have my own notes open. That's what I was saying earlier. I'm going to give you the right directions. The grid notes in the PDF are going to be incorrect.
And again, file in X direction because you're collecting at some spacing in the X direction while you're moving in the Y direction. And is that why you're filing it? Okay.
Correct. Yeah. Each file moves back and forth along the x-axis, and each transect goes up higher and higher in the y-axis. So then we'll hit next. We are going to change the order that the files were collected in. This was a zigzag grid, so zigzag still in the bottom left-hand corner. So we want to select the option, the fifth option, that has the small black box in the bottom left-hand corner, but the arrow is pointing in every other direction. So we'll hit next. And then if you look at this, what we should see are profiles spaced 50 centimeters apart, and we do. And they're all about 20 meters long. A little bit longer than 20 meters. So then we'll hit next. It asks if we want GPS coordinates. I don't have them here, so we'll just hit finish. All right. So we now have our Etowa grid open. This, to give you some background, this is a data set that was collected at an archaeological site. So the intention for this grid and the reason why it was unidirectional is we're not necessarily looking for pipes or targets. We're looking for archaeological features of interest. Specifically, we'll see a couple of artifacts littered about. We'll see a pathway, and we'll also see the foundations of some old structure. So definitely a lot of interesting targets, but nothing necessarily hyperbolic. So it might be difficult to do a migration. It's not imperative to do a migration here, but all of the other processes that we've discussed are processes that we'll most likely want to do. If you look at the file header and just see what's already been done, we see that this is SIR 3000 data. This was collected with a 400 megahertz. And as far as processing goes, there's been some range gain. There's also been a low pass, high pass IIR filter, and that's pretty much it. So
can we remove this, all the processes that has been done on this file?
We cannot with SIR 3000 based data. When you collect data on the SIR 3000, the processes are stored in with the raw data. With our newer systems, they're stored separately.
Okay, thanks.
Yeah, no problem. So there's been some processing done to this already. As I said before, it doesn't hurt to do the IIR filters again, but for the most part, we're going to be just throwing as much at this as we can. So I'm going to go through and slowly process this grid. If you have any questions or if you're unsure where to go next, just let me know in the chat. If you keep an eye on my screen, I'll touch on the processes that I think are worth doing here. But feel free to attempt some of the other ones that we've discussed. If you want to try Hilbert transform, if you want to try deconvolution, there is definitely some ringing in here that we can try to use that to remove. If you want to try some of the other processes that we haven't touched on in a while, you can do that as well. I'll touch base with you in about, we'll say 10 minutes or so, 10 or 15 minutes. This is a pretty big grid, so it's going to take a really long time for these processes to run. So don't forget to open the tables pane and the file header to speed your processing up. But again, I'll touch base with you in about 15 minutes as we go through and process this grid, and then we'll talk about what we see. But let me know if you have any questions in the meantime. All right. So to get to this last 3D view, there are definitely a few routes that you could take. I took a slightly different route than what I normally do by starting with time 0. You're going to have to start with time 0. And then after that, I did a deconvolution and then a background removal to finally get it ready for its view. You can also do IIR background removal, some range gain. I've done range gain in the past. There are some slightly hyperbolic features, so a migration is difficult but not impossible to do in this data set. So there are definitely quite a few processes that you can throw at this to still get a good final picture. You don't necessarily have to do the route that I did. But regardless of which route you go down, when you look at this in 3D, you should start to see some features. As I slice up and down through it, right in like the upper third, you should see this big square-ish feature here. So this is the foundation of a structure that this survey was primarily done to locate. I believe this is an old animal pen in the area. And then if you go up a little shallower, you might have noticed I tried to highlight these really bright features here, which you probably saw in the GPR data as well. This bright target that rings all the way down through that lines up with this roughly circular feature here, and then another one over here. These are, if I remember correctly, old storage pits in the area. Basically holes in the ground that were dug and filled with artifacts of interest. It could be food, it could be personal items, but these are storage pits in the surrounding area. And then if you go very, very close to the surface, you might see this bright line that cuts the whole grid in half. This is actually a walking path in the park that this was collected in. Etowa is a region, I believe in Georgia in the United States, and it is publicly accessible. And I believe this is a walking path that just cuts right through the park. So you can see the compressed earth here, and unbeknownst to the visitors here, there were some objects of interest just off the side of the path on either end, really, the storage pits on the left and the foundations of a structure on the right. So pretty cool. But any questions about this while you were processing it, or anything that you ran into?
Kevin?
Yes.
So for some reason, I'm not being able to use this cursor to move that z-axis, up and down.
The Z-slice?
Yeah.
So I do this by holding the control key on my keyboard.
Oh,
and
okay.
Click and drag on this slice to move it up and down.
Okay, cool. Yeah, cool. I got it.
Yeah, without the control key, you'll rotate it, but with the control key held down, you can move the walls and the floor of your grid. Okay. Okay.
So how often you use this Hilbert Xform? Is it very useful tool, or how often you use?
Honestly, I don't use it that frequently. It's a cool process, and it's used by us often when we're showing you data on the control units. But in practice in RADAN, I don't really use it that much. And primarily it's because I make a lot of my assessments by looking at 2D data, and the 2D data ends up looking so much different after it that it becomes unusable to me. So I usually don't use Hilbert transform, but if you are getting ready to create a picture for a client and you're not going to be analyzing the 2D data anymore, that might be a good point to tack on the Hilbert transform to get your 3D view looking nice and then getting the picture for your report. But beyond that, I personally don't use it that much.
Kevin, I have a question.
Sure.
So when we processed that scan and we pulled all the files into the grid, we had the lowest number at the top and we went down to the highest number, correct?
Correct.
Because when I look at my 3D scan and I look at your 3D scan, your triangle thing that you have in the top right is like on the bottom left of mine. And I swear mine was in the same order yours was in.
You may have checked files in the Y direction instead of X direction, which might have put them in a different orientation. It would still make an okay picture. It would just switch where everything is.
Okay, so if I were out in the field collecting these scans, I want to start on, let's say, the right-hand side and move left to take my scans.
So the way that RADAN will understand your grid most easily is if your origin point is in the bottom left-hand corner. So this doesn't necessarily mean that you need to start in the southwest corner with respect to compass directions. But
Okay.
this does mean that when you're visualizing your grid, your
Mhm.
first scan should be moving away from this location, whether you're going to the right in the X direction or upwards in the Y direction. You should always be moving away from this and consider that as your starting point, your origin point.
Okay.
Okay. So at this point, we have touched on all the material that I intended to cover for this class. So now we get to the open floor part. If you are comfortable with what we've covered so far, you are welcome to sign off at this point. Thank you so much for spending time the last couple of days with all of us processing some data. I will reach out to you with your training completion certificate, as well as a link to download these sessions if you want to review them at a later time, a little bit later on today. So you should be getting an email from me later on today with all of that information. If you want to stick around and ask me some more questions or look at some of your own data or talk about some of these other processes, that's what this time is for. So I will now open the floor up to any other questions, and I'll stay online until we don't have any more. So let me know. It'll be first come, first serve, and I will just answer your questions one at a time. And you can let me know it either in the chat or by unmuting yourself. Either option is totally fine.
Kevin,
Hey.
I'm a little bit unclear about this Hilbert Xform. Do you mind just going through it quickly, like a minute or so?
Sure. So, what the Hilbert transform really does is look at the. So if you look at this scope representation here, if we look at like this, or here, let's go to a better target. Yeah, so if you look at this target here, This is actually a hard data set to do this with. Let's just open a different file. Maybe just pit. So if we look at this pit file here, and we see this reflection over here, this target, the reflection from this target is this here, this negative, positive, negative band. What the Hilbert transform does is it has the ability to recognize that this entire thing, this negative, positive, negative band, is all coming from one target, one feature. And so instead of showing it to you with multiple different polarities, by polarity I mean negative, positive, and negative, it flips it all onto the positive side and shows it to you as a uniform positive hyperbola instead of a negative, positive, negative hyperbola. If we actually open the process and hit the apply button, you'll see that our hyperbolas no longer have negative polarities to them. They turn into these roughly uniform positive arches. And that's the intention of this process. Its primary goal is to run this off of data that's been migrated already so that it's focused into a dot. And then instead of getting a dot that has a little negative dot above it and a negative dot below it, it'll make it look like a uniform positive circle. And the really only intention of this is to make it easier to look at in 3D. It doesn't really do much else for you.
It has few other options, phase and frequency. So is there anything we mess up with that, or just leave as it is?
Only do it with magnitude. The other two transforms are not going to be helpful to you. Phase will just make everything that's a little bit positive very positive, and everything that's just a little bit negative very negative, right? So it just takes everything to its extreme. If the scope goes a little bit one way or the other, it moves it all the way in that direction. And if I'm being perfectly honest, I've never gotten a clear answer as to what the frequency transform does, so I can't even begin to tell you what it'll do. That information seems to no longer exist in the company, so I don't know what frequency does, and I've never had to use it, so I don't think you'll have to use it either.
Okay. Thank you, Kevin.
Yeah, no problem. Okay. Well, if there are no further questions, then I think we'll just end class early. Thank you again for sticking around. Thank you again for spending some time with us this week to process and learn more about RADAN and how to post-process your GPR data. As I mentioned at the top of the class, my name is Kevin O'Hara. I'm part of the technical support team here at GSSI, as well as our training team. If you have any questions at all in the future, I'm going to send you an email after this with your certificate and links to download the recordings of this session. My email and direct line will be there. So if you have any questions at all, feel free to write me an email or give me a call, and we can discuss. If you're trying to reach me and I am not getting back to you quick enough, it might be because I'm doing another one of these sessions. So if you need an answer right away and you can't get a hold of me, you can also always call GSSI's main number and dial 3 to get on the technical support queue. That'll toss you around to my colleagues, one of which should be available to help you during our normal operating hours. So thank you again. It was great to meet you all, and I'm sure I'll talk to you again in the future. So hope you have a great rest of your week. Let's say, so we've covered a lot of ground in the processing pane. We've talked about a good number of the processes here, which will definitely prepare us for the grids that we're going to take a look at tomorrow. We're going to be doing a lot of these processes in great detail over the course of the day tomorrow. So we'll definitely be revisiting time zero. We'll be revisiting IAR and FIR. We'll be revisiting, background, migration, range gain over the course of our 3D grid analysis tomorrow. So we'll definitely have plenty of time to practice these then. I have a couple of other processes that I think we'll touch on tomorrow as well. But for now, I think we've covered all that I intended to cover for today.